For today, I think we will discuss mainly from your latest book, which is titled Modern Software Engineering. The first thing that comes to mind for me when I look at the title, why do you call it modern software engineering? Is there the old ways of software engineering and there's a new modern way of software engineering?
Yeah, it was a title that was stuck in my mind for a long time while I was writing the book. And to be honest, I was somewhat nervous at the title. The reason that I call it modern software engineering rather than just software engineering, and I was nervous of the title, is kind of the same. I think in our industry, we've kind of weirdly devalued what we think of as engineering. I think it's very common to think, for people to say, software development isn't engineering. And a lot of it isn't. I think that's fair. A lot of it isn't engineering. But in other disciplines, engineering doesn't mean heavyweight bureaucracy, which I think is what it tends to mean to us. What engineering means in other disciplines is the most effective, efficient way of doing work of high quality. And so if software engineering doesn't allow us to build better software faster, it isn't software engineering. So modern software engineering, I think, is different to what went before. We've tried to implement engineering approaches before, and they were nearly always narrowly focused on some particular set of tools or diagramming techniques or something like that, and bureaucratic and heavyweight. And that's not what I mean at all. So I mean almost entirely the opposite of that. So what I was interested in, part of my background and interests, my hobbies, is that I'm very interested in science. I think that a reasonable definition of engineering is as a practical implementation of science. You apply scientific style reasoning, which is humanity's best approach to learning, to solving practical problems. And I think that's a reasonable kind of colloquial definition of engineering. I was interested in those kinds of ideas. What are the ideas that we could point to, and whatever your technology, whatever the problem that you're solving, whatever organization that you're working, if you applied these principles, you'd have a better chance of success. And I thought I'd spotted some of those things over time. And they're related to continuous delivery, which was my previous book that I worked on with Jez Humble and so on, but also somewhat separate. It's a slightly different angle. It's kind of orthogonal. They intersect and they're very reinforcing of one another, but they're not the same idea. So what were the principles that would allow us to do a better job? And I thought that was what I was trying to explore, and that's what the title was meant to try and convey.
The subtitle of the book itself is Doing What Works to Build Better Software Faster. And in your book, I also find it quite insightful is that you mentioned that if our software development practices do not allow us to build better software faster, we should really change them because they are not engineering. Yes. So please tell us more about this concept. Why do you think so? Like why we should focus on building better software faster?
Well, the simple answer is why would anybody want to build worse software slower? I think it's the combination. In part, this is my kind of, again, colloquial take on the DORA metrics, the metrics that come out of the State of DevOps report that give us a predictive model. If you work in these kinds of ways and do these kinds of things, you increase your chances of success. And they are based on the stability metrics. What's the quality of our software? When we introduce software into production, how often does it break? And when it breaks, how long does it take us to recover from the breakage? And throughput. What's the efficiency with which we can deliver software of that quality? So that's the faster part. So working quickly, one of the findings from the DORA metrics, which is important, I think, is that there is no trade-off between speed and quality. One of the traditional assumptions is that if you want to build high-quality things, you need to go slowly. What the DORA report says is no. If you go slowly, you build lower quality things. And that's what the statistics say. That's what a sociological approach to measuring the performance of software development teams finds. The more barriers you put into being able to release change quickly, the worse the output. So we want to be able to move quickly, we want to be able to go faster, and we want to be able to build better software. And that means that we need to be able to focus on being able to learn, find out where our mistakes are, correct them really quickly and efficiently. And that kind of is one of the ways in which this plays in with continuous delivery. Continuous delivery is a fantastic way of being able to build better software faster.
From my career itself, I can tell that so many experience from my view is that we build software faster in the beginning, but turns out after a long period of time or maybe a few months, it starts to get slower and slower. And maybe many people have left. They don't know about the context, the domain problems. So I think maybe some of the tools that we will discuss today can help people to really build better software faster, like continuously. So you have a definition about software engineering, right? If I can read here, is that the application of empirical scientific approach, which you mentioned in the beginning just now, to finding efficient economic solutions. So the economic solutions here is also quite interesting to practical problems in software. I know that you cover in the book that some of these keywords are really important. Maybe if you can discuss slightly some of these terms, why do you think it's important to define software engineering using this way?
So I was trying to get the simplest, minimal description of what I was thinking in terms of engineering. I was quite pleased with that description that you just read out because it's fairly lean, it's fairly concise, but I think it doesn't miss anything important. So applying the reasoning, the rational approach of science, I think that one of the fundamental natures of science is that the differences between science and almost everything else is that we start out assuming that we're probably wrong. And that's a very healthy thing to do in engineering and in software development at all. So we're going to apply scientific style thinking in a light way, not overburdening, not bureaucratic way, but we're going to be informed by that kind of thinking. We're applying that to solving practical problems. We're not doing theoretical research and proving that quarks are the basis of particles or anything. We're building things. And so we've got to be practical and pragmatic. So the empiricism of engineering, just trying stuff out ultimately, is a big part of it as well. The economic part is, again, part of engineering. If we are physicists, we can imagine building machines out of black holes. Thinking about that practically, economically, in energy terms, we're not ready to do that kind of thing. For us engineers, we are building things. And so there are always economic constraints at some level. That's about the amount of time and effort and money that we spend, but also economic constraints in the sense of the performance of our delivery system and the performance of our software, the carbon footprint of the software that we create, that kind of thing is an interesting question in its own right. So I wanted to get that in there as well. So I think all of these different parts of the definition kind of lead us in this direction of trying to organize our thinking in a more rational way and apply it to solving problems that are of value to people in some way. That's what I was trying to reach for with the definition.
Thanks for that explanation about the software engineering. So I think for us, we need to probably redefine some of our understanding. Software engineering is not just writing code that works and deploy it.
I think that's a really good point. One of the things that I'm obsessed with at the moment is watching SpaceX build their space rockets to go to Mars. That's engineering live on YouTube. You can kind of watch it happening in the real world. That's not theoretical. They're evaluating their ideas. They're blowing spaceships off. They're learning from that. They're making progress step by step. And I think all of these things kind of come into an engineering approach to solving problems and thinking about the ways in which stuff can go wrong, and all of the time looking at how to improve and refine our designs and our solutions so that they'll better fit the problem that we're trying to solve.